start. Okay, so today we were continuing with modular arithmetic. We didn't really get to it last time, but I tried giving you real quick some intuition for what it would be. So, starting with the sets that we're going to be doing arithmetic on. So we start with this definition. When you see z sub n, that's the subset of integers from 0 up to n minus 1. So z sub 10 was 0 through 9. And we were going to do arithmetic on these kinds of sets. So we talked about plus and times last time, but let's look at their definitions again real quick here. So if I have two elements in Zn, whatever Zn is, then we define A plus B to be the regular sum mod n, and A times B to be the regular product mod n. And this worked almost exactly how you expected it. So if I said if we were in the context of Z10, and I asked for 9 plus 9, then that gave us 8, exactly. What about 19 plus 9?
8.
Undefined. 19, what's that?
Right.
So careful. The only things that this makes sense for are numbers in the set Z10. And then multiplication worked much the same way. If I was talking about 9 times 9, what does that equal?
1.
1. Right? 81 mod 10 is 1.
All right.
So those two work as expected. It gets a little bit, well, even subtraction works exactly as expected. It's when we get to division that we'll run into problems, but let's focus with just plus and times for now. So what are the properties that these things have? They have all the properties that you expect them to have. As long as n is greater than or equal to 2, the only reason that we're saying for n greater than or equal to 2, that's the n that we're using here, we're saying this set has at least 0 and 1 in it. Then it has these properties. The reason we need it to have 0 and 1 is because we're going to explicitly mention 1 and 0 in these properties.
Okay.
So it needs to have 1 and 0 for us to talk about 1 and 0 set. These properties hold for n greater than or equal to 2. If you have 3 arbitrary elements in Zn, a plus b is equal to b plus a, and a times b is equal to b times a. They're commutative. A plus b plus c is equal to a plus b plus c, and same with multiplication, they're associative. A plus 0 is equal to a times 1 is equal to a, and a times 0 is equal to 0. And then finally, we can distribute with these the way that we expect. A times b plus c is equal to a times b plus a times c. And these are properties that you're going to prove in your homework. I'm sure I'll make you do a couple of them. I don't know which ones. The first thing I'm going to make you prove is that these are closed. Now, what it means for an operation to be closed is it gives you elements in the set. So, if I take an element from Zn and I add it with an element from Zn, the result is an element from Zn. Right? Which is pretty obvious because it's going to be a plus b mod n. It's the remainder. When you add these, the remainder is always between 0 and n. Therefore, it's in Zn. Oops, did the proof. Same with times. It's a closed operation. If a and b are in Zn, then a times b is in Zn.
Isn't that kind of proving, well, what would be an example where it's not closed?
If you wanted to use division in the sense that you know division on the integers. 4 is an integer, 3 is an integer, 4 divided by 3 is not an integer. But it is closed on the rationals. Rational divided by rational is rational. Rational, yeah, just leave it at that. Anyways, okay, so let's do a quick proof that this plus is associative. It looks like a lot of messy stuff keeping track of your numbers, but it's really not very complicated, so stick with it. If it feels like it's getting confusing, make me re-explain, because it's really kind of simple. So we're going to prove it's associative. So we've got three elements, A, B, C, and Z, N, and we're trying to show that it's associative. So in other words, I'm trying to show that, which one did I start with? I'm trying to show that this is equal to this, right? So I'm going to start with one, show it's equal to the other. Now, I know that whatever this thing in is an element of Zn from this proof right here. This is an element of Zn. This is an element of Zn. This is an element of Zn. Good? Okay, so then what does this thing equal? What is A plus B plus C equal to? Well, that's going to be A plus B plus, remember, what is B plus C?
It's B plus C mod n.
It's B plus C mod n, which is the remainder, right? So it's going to be what you had minus some, or plus some multiple of n. How can I think this makes better sense with a quick example. For example, when we said, what was 9 in the context of Z10? 9 plus 9 was equal to 9 plus 9 mod 10, right?
Mm-hmm.
Which is 18 mod 10, which is, you know it's equal to 8, but we could write the remainder. You remember that theorem where you take two integers and when you're dividing, then if I'm doing A divided by B, not divide in the sense that we're going to talk about later here, but we could always write any integer as A times QB plus R, right? And this R is what we meant by mod.
Mm-hmm.
So R can be rewritten as whatever you're modding minus some multiple of what you're modding by. This is Q, right? So when I have 18 mod 10, then we're saying that is 18 is equal to 1, 10 plus 8, right?
Mm-hmm.
And so what it equals, 8, can be rewritten as what we started with, 9 plus 9, plus some multiple of what we were modding by. So in other words, I'm saying I can write 8 is equal to what we started with, plus some multiple, in this case 1, multiple of 10. That's what I'm saying here.
Isn't it minus there?
Oh, minus, but we could make this a negative 1 in here to
Right.
keep it up. Yeah, some multiple of 10. So that's what we're doing from here to here. You need to get comfortable with this because this is what you're going to do over and over again. What is B plus C mod n? It's B plus C plus some multiple of n. What is 9 plus 9 mod 10? It's 9 plus 9 plus some multiple of 10.
Okay.
Because you can't use an actual number here,
And
so
it's
you
just
need
a
a way to
negative.
represent it.
It's a negative multiple.
In this case, it's a negative, well, could be a negative, could be positive.
What's the case where it would be positive?
I'm thinking when we're minusing, but Zn always has to be positive here. So, you might be right, K might always be negative in this case. So in this case, I think K will always be negative. But anyways, important is understanding how I went from B plus C mod n is the exact same thing as B plus C plus some multiple of n. Does that make sense?
Mm-hmm.
This is generically how you're going to have to handle it over and over again when you're trying to be generic about these, when you're doing proofs with these. So you've got to get comfortable with that. And it throws a lot of variables in here, but the idea really isn't that hard once you understand it.
Okay.
Okay. So once again, exact same thing. What is A plus this whole thing? It's A plus that whole thing plus a multiple of n.
Okay.
Where can you are two integers. Now I'm going to use the theorem that you guys proved, I think, 2 weeks ago. in your homework. If I have a plus b plus c, okay, first off, note that this is just rewriting this over here, and I'm grouping my n terms together.
Okay.
Okay? So I know that this is equivalent to this mod n, right? Because what's this mod n?
Some multiple of.
It's 0.
What do you mean? It's zero.
Any multiple of n, mod n, is 0. So for example, what I'm saying here is 8 plus 10 is congruent to 8 mod 10. 8 plus 20 is congruent to 8 mod 10. 8 plus any multiple of n here, 8 plus any multiple of 10 here, in this case it's 10, is still going to be 8.
Okay.
Mod n. This is using our equivalent mod n. You remember this?
Yeah.
This is all the numbers whose remainder would be 8 mod 10. This is one of those numbers. So, this is equivalent to this mod n. Why? Because this part doesn't make a difference. This is just a multiple of n.
Okay.
It's just some number times n. You with me on that?
Yeah.
Okay, and then you did a proof last time that if A is congruent to B mod n, then A mod n is equal to B mod n.
Yeah.
Those are logically equivalent. You remember that proof?
Yeah.
That's how we go from equivalence mod to using mod in the sense that we want to use it. Just writing it in short terms here. A congruent to B mod n. This was logically equivalent to, these two things you can interchange between. A mod n is equal to B mod n. If this is true, this is true, and if this is true, this is true. Remember that? Okay. So that's what we're using here. So since this is congruent to this mod n, then this thing, mod n now in the sense of the remainder, not the equivalence class, is equal to this mod n.
Okay.
You good?
Mm-hmm.
Maybe I should have jumped shortcut where we were trying to get with all this and then filled in the blank. Where we're trying to get is a plus b plus c is equal to a plus b plus c mod n. I'm going to show that this is true, and then that this is true, and therefore they're the same thing. That's the easiest way to do it.
Okay.
I'm trying to show this is equal to this. I'm going to do it by showing this is equal to this, and then this is equal to this, until those two are equal. That's ultimately where I was going with this. I probably should have motivated that better. So that's what we're trying to get. We're trying to get this is equal to this thing, mod n. So here's where we were. So if this is true, then this is true. Right?
Mm-hmm.
But this is this number. In other words, when you mod this by n, you don't change it. How do I know that when you mod this by n, you don't change it? Because this is an element in Zn.
How do you know?
We've just written out what it is. This is an element in Zn. What is this? It's this. So this is already an element in Zn. So if I mod it by n, I don't change it. In other words, this is 8, where we erased what I had before. But 18 plus negative 1 times 10 is already 8. When I mod this by n, I don't change it. I still have 8. This is a different way of writing 8, and it's a convoluted way of writing 8. But it's still just 8. Modding it by n doesn't change it. If this were 18, modding it by n changes it. But since this is already in Z10, modding it by 10 doesn't change it. I'm still just going to have 8.
Right.
That makes sense?
Yeah.
So this value right here is already a member of Zn. So when I have it, and I mod it by n, it doesn't change it.
Oh, right. Okay.
Okay? That's what I'm trying to get at, so finally I can do a substitution back. So this is already in Zn, it was just another encoding for this. So this this is equal to a plus b plus c mod n.
Okay.
So kind of a roundabout way of doing it. We were substituting in to get exactly what it was. We knew that that was at least equivalent to this mod n. Use that term that you guys used last time, and then use the fact, okay, we didn't actually change this side. So we didn't change that side. That's what we had the whole time. So the only reason that we expanded all that out is so that we can start by saying this is equivalent to this mod n, and then this is equal to that mod n. So a lot of work for something that can be said pretty simply. And then we could have done the exact same thing with this. I didn't think there was any point in doing it all over again. So good to understand the proof? All right. So that was proving one of these properties. All the proofs, kind of similar ideas. I don't know. I will be here after school, by the way, so.
I had a question about that. There's some people in the trig class who are wondering if they can come to that.
They can come, but I'm going to have priorities that I have.
Okay.
And it would be prioritize you guys, then there's another student I committed to, then whatever leftovers there are.
Okay.
I'm guessing the other student I'm committing to is going to need as much as I can give. Because they're doing calculus at the college, and
Is that Emma?
yeah, she's doing calculus and she hasn't done trig yet, so.
Yeah.
Okay, that covers that. So now let's talk about subtraction. Subtraction, we could define exactly how you want to define subtraction. You probably want to define subtraction as just do a minus b mod n.
Or a plus negative b. But you can't do that in this case, because it's,
What do you mean by negative b?
well, negative 1 times.
Negative b is not in there,
That's what I'm saying.
so you can't use negative b. Okay, so you might have tempted a minus b mod n. You could define it that way, perfectly valid way to define it. We're going to define it this way, and then show that's the same thing as defining it a minus b mod n. We could have done the exact inverse, and we could have said, defined it this way, and showed that this is also true. Either way, we need to know both these facts. So it doesn't matter which one you define, which one you prove.
Okay.
Pick one's your definition, pick one to prove. Same work either way. So we're going to say that a minus b is the unique number in Zn, call it x, such that when you add x to b, you get a. What's a minus b? It's the number you have to add to b to get a. That's what a minus b is. Make sense?
Yeah. Yeah.
So there's two things that we need to. Well, no, we'll leave it at that. So now let's prove that this is logically equivalent to this way of defining it. So given that a and b are in Zn, we're going to prove that a minus b is equal to a minus b mod n using this definition.
So, my question is how if b plus x is positive. Oh no, that makes sense. Okay, I got it.
Good?
Got it.
Okay. So we need to show that a minus b mod n, first of all, is in Zn. And then we need to show that if x is equal to a minus b mod n, then x is the number that satisfies this. You with me? First we need to make sure this is in our set, and then we need to make sure that whatever it is satisfies this equation. So if it's in our set and it satisfies this equation, then it works.
Okay.
Because we're trying to show that this is the same as this. So if this is in Zn, and if this satisfies this equation, then this is logically equivalent to this.
Okay.
Make sense?
Mm-hmm.
That's our thinking. Okay, well, a minus b mod n in Zn, obviously, since anything mod n has to be between 0 and n. It's the remainder.
Shouldn't it be n minus 1?
If I did a less than or equal to, if I just did less than.
Oh, right. Okay.
R is in between 0 inclusively and B exclusively, right?
Right.
Okay, so obviously A minus B mod n is in the end. Next part. Let's see if this satisfies the equation. So if I let x equal A minus B mod n, does it satisfy that equation? Well, if x is equal to A minus B mod n, then x is equal to A minus B plus some multiple of n. Same exact thinking we did over here. Where did we do it? B plus E mod n is B plus E plus some multiple of n. A minus B mod n, lost track of where I was. A minus B mod n is going to be A minus B plus some multiple of n. Is that weird? Is that weird, Lee?
Kind of. Can you just explain it again? Like, I know we did went over this already, but.
So A minus B mod n is the remainder when you take A minus B and you divide it by n. So let's write that out. So A minus B divided by n is A minus B is equal to some multiple of n plus what we're solving for, r. It's the r in this equation. A minus B mod n is the r.
Right, right.
And r can be rewritten as A minus B plus some multiple, some different multiple in this case, of n.
Right.
That's good. Let's go over that anytime it feels weird.
A minus B divided by something, or is it just A minus B?
It's the r. Just move this to the other side.
What I'm saying is, you've used A minus B. Wouldn't it be A minus B divided by some other thing?
When I say A minus B mod n, then that's the remainder
Okay.
when you write A minus B in terms of, when you write A minus B this way.
Okay. Okay. Yep.
Try not to say divide, but I don't know what else to call it. That first theorem, I told you that first theorem that we did was going to be the most basic thing we use in number theory over and over and over again. And probably the second most common theorem that we're going to use is the A x plus by equal to 1, 1.
Equals 1.
Yeah.
What is the equals?
Equals the greatest common divisor,
Yeah.
but we were specifically interested in the case where they were relatively prime and it equaled 1. And
Okay.
we'll see that come up again too. Anyways, continuing. So you're good with this step. A minus B mod n, if x is equal to A minus B mod n, then x is equal to A minus B plus some multiple of n. Right? It's the definition of A minus B mod n. It can always be rewritten that way. It's probably a better way to say it. Okay. So then B plus x, remember, B plus x better be A. If we define x to be A minus B mod n, then B plus x better be A, and then it satisfies our definition. X has to be the unique number that you add to B such that you get A. So, B plus x then is B plus A minus B plus Kn, B plus x mod n. That's the definition of this addition, right? And then B's cancel out. Right? And what is Kn mod n?
It's just 0.
0. So, it's equal to A.
So it's not A plus Kn mod? Wouldn't it be A mod n?
Well, A is already in Zn.
Right.
So A mod n
I
is
just want to make sure that I have
A.
it in my head right. So, right, so A mod n is A, but that's technically saying A mod n before you get there, right? Does that make sense?
We already know that A is an element of Zn.
Okay, yeah, I got it.
Okay. Any other questions about that? So, you can think about however you want. You can think about this A minus B as A minus B mod n, or you can think about it as the integer in Zn that satisfies that equation. Good? Okay, so we've talked about addition, we've talked about multiplication, we've talked about subtraction. Now let's talk about division. And we need to see the problem that we're going to run into with division. So here in regular multiplication, with like the integers or the real or whatever, if you have a times b equals a times c, then you know that b equals c. Right? And how do you get from this to this? You divide both sides by a is the way you might say it. And the question is, can we do like a similar operation with times? If a times b is equal to a times c, does that mean that b is equal to c when we're doing modular arithmetic? And the answer is no. So here we're in Z10. 5 times 2 is in Z10. 0. 5 times 4 is 0. 2 is not equal to 4. Those are two different elements in Z10. So we can't use this same type of thinking with division, or with multiplication for some reason. And the problem's going to come down to defining division is a bit trickier than it might seem at first. So maybe we think, all right, let's try and define division kind of like we defined subtraction up here, right? If we define a minus b to be the x that makes b plus x equal to a, maybe we can do a similar thing with division. Maybe we can make a divided by b is the unique x in Zn such that a is equal to b times x. Makes sense, right?
Yeah, well, if you're just using that, but is it actually true?
Is it actually true? Let's try it. Let's think in Z10. In Z10, let's say we want to do 6 divided by 2. Well, it turns out there's going to be two answers to that then. Because 2 times 3 gives you 6, and 2 times 8 gives you 6.
Okay.
So what's 6 divided by 2? Doesn't work for some reason.
Unless you find a way to throw out the wrong answer.
Yeah, but then why should one of those be more right than the other? I mean, there's not really a right and a wrong answer. It's just not well defined. We're getting two numbers.
So we need to narrow down the definition somehow?
Yeah, we need to narrow down the definition somehow. And if you were to try all the numbers, you'd find out sometimes you could divide it and using the same thinking that we have, and it would work. And sometimes it wouldn't work. So why can we do the types of thinking that we do up here with numbers in like the rationals, but we can't do it with our numbers? What's wrong with our number system? Why can't we do this division? Well, inside the rationals, when we define a divided by b, we actually define it as a times the multiplicative inverse of b. That's how we actually define it now. You guys are
another way to define it?
not going to be a great way to define it if you define it in that way.
So that
Pretty
that's
standard way to
basically
define
the
it.
way that we define it then. Okay.
It's so we refer to 1 as multiplicative identity and 0 as the additive identity. So you have plus and multiplication defined, and you have what's called the additive identity 0 and the multiplicative identity 1. And then we define
So the division identity is this.
we define division this way. Sorry, we define b inverse to be the unique number such that b times it gives you the multiplicative inverse 1. And similarly with negative numbers, we define negative a. What's negative a? It's the additive inverse of a. It's a number that when you add it with a, you get the additive identity, 0. So, yeah. So, when we're defining division, we define it to be a divided by b to be a times the multiplicative reciprocal of b. In this case, we're just going to say the reciprocal. In other words, b inverse is a number such that b times b inverse gives you 1. In other words, that's not in other words, but that's just more explanation. I don't know why I said in other words. Anyways, so we're going to have a similar idea of division when we define division in terms of our modular systems. We're going to define a divided by b to equal a times the reciprocal of b. So we are going to define it the same way, but now we need to come up with a definition of what exactly we mean by the reciprocal.
Yeah.
So that's what we're going to define here. So let A and Z in. Then B is a reciprocal of A if and only if their product is 1. Which makes sense,
Yeah.
right? And then an element of Zn that has a reciprocal we call an invertible element.
If it's not invertible, you can't do division on it.
And if it's not invertible, you can't divide by it.
Okay.
So the last thing we're going to need to do is prove that it has one, and if it has a reciprocal, then it only has one reciprocal. And so we can use this symbol. Because when we say B inverse, we mean the one and only one inverse of B. So that's why we didn't say A inverse here, because we don't know that there's an A inverse. Yeah, you see what I'm saying? Why did I do A times A inverse here? Because there might be multiple B's that make this true. Later on, we're going to prove that there's only one, and we're going to call that special B A to the power of 1. Okay. So let's look at Z10. Let's make a multiplication chart for Z10 and find the inverses of numbers. So here's our multiplication chart. And remember, A and B are multiplicative
Reciprocals, please.
B is a reciprocal of A if and only if their product is 1. Okay, so here's our times table chart for Z10. 0 times 0 is 0, 3 times 4 is 12, mod 10 is 2, etc. And I put in pink all the times where we get 1. So in other words, 1 has a multiplicative reciprocal and it's 1. 3 has a multiplicative reciprocal and it's 9. 9 has a multiplicative reciprocal and it's, oh, oops, that's 7, not 9. 3 is paired with 7, and then finally 9 is paired with itself.
Would you also need to say that 7 is paired with 3?
Well, you can.
I mean, just wondering if that's necessary.
Well, we're just having a discussion, so whatever makes it clear to you. So, and it makes sense. 1 times 1 gives you 1. 3 times 7 gives you 1. 7 times 3 gives you 1. 9 times 9 gives you 1. No other ways can you get 1. So that means in Z10, these are the only numbers that we would know how to divide by. So 2 divided by 3 would be 2 times 7, in other words.
Mod n.
Mod n, yeah. So
That's cool.
So it's very unintuitive how
Yeah, that makes
division
sense.
works. It's the least intuitive of them all, but that is how it works. So here's a multiplication table, and these are the only ones that had multiplicative reciprocals. One of the things to notice, and I think we'll prove it later, is that, so let's look at the numbers. The numbers that have a multiplicative reciprocal are 1, 3, 7, and 9. What do you notice about those numbers? And we're in
They're all the odd ones in Z.
5's in there.
Oh yeah.
Why doesn't 5 have one?
Those ones are.
They're not just all the primes, they're not all the odds. Although you'll notice all the primes are in there, we just have things that also aren't prime, with the exception of 2.
Well, 5's not in there. 1 is in there.
Oh yeah, never mind. Sorry. I was thinking weird for a second.
9's in there.
You notice anything about those?
They
1, 3, 7, and 9.
10.
They add to be
The
10.
pairs do, so 9.
Okay, that might be a coincidence. That's a little interesting. Have to think about that. Let's look at the numbers that aren't in there. Kind of ignore 0 because obviously 0 is not going to be in there. Let's see. 2, 4, 5, 6, 8. Is there something that these numbers have with respect to 10 that these numbers don't have with respect to 10? What did we do last week?
The even numbers, when you divide 10 by those, you always get something else in there. I mean, not just the even numbers, but not lower side. So like 10 divided by 2 is 5, 10 divided by 8 is 4. Well, I guess, but I mean, I guess that doesn't really matter.
What did we do last week? Greatest common divisor.
Yeah.
What's the greatest common divisor of any of these numbers with 10? 1. What's the greatest common divisor of any of these numbers with 10?
2.
Depends, right? 2, 2, 5, 2, 2. So these are the ones that are relatively prime,
And those ones aren't.
and these ones aren't.
Oh, okay.
And that turns out to be the case when they are relatively prime, and we're going to have to prove that as soon as we're done with this. I'm going to have to erase whiteboard to that proof. But it turns out that's going to be the case. If the numbers are relatively prime with the system that you're in, then they're going to have an inverse. And if they're not relatively prime, then they're not going to have an inverse. Make sense?
Mm-hmm.
So we'll do the proof of that, but that's something I want to know while I have the table all written out up here. Okay. So, continuing, let's just prove. So if we have A and Z in, if it has a reciprocal, then it only has one. So numbers that have a multiplicative reciprocal only have one. So 7 has one reciprocal, 3. I only got one showing up for 7 once. So it either shows up 0 times per number or once per number. Showed up once for 9, no times for 8, once for 7, no times for 6, no times for 5. None, 1, none, 1, none.
Okay.
See what I mean?
Mm-hmm.
So we're going to prove that if it has one, if it has a reciprocal, then it only has one reciprocal. A number can't have multiple reciprocals. So in other words, the reciprocal of a number is going to be well defined. It's going to be a particular number. So we can always talk about the reciprocal of a number as a number. Does that make sense?
Yeah.
Okay, so that's what we're going to prove here. It's actually a really easy proof. So, assume by way of contradiction that there are two numbers, B and C, in Zn, such that A times B gives you 1 and A times C gives you 1, but B and C are not equal to each other. Right? That's what it means for B to be a reciprocal of A and C to be a reciprocal of A. Their product gives you 1. But they're not equal to each other. Well, then what does B equal? B equals 1 times B, using our property over there, multiplicative identity. Here's another way of writing 1.
Okay.
Right? Times B. Use associative and commutative properties to reorder it, so we have C times A times B. What's A times B?
1.
1. So you have C times 1, which is C. So you have B is equal to C. Contradiction. B is not equal to C, B is equal to C. Doesn't work.
Okay.
These are the kind of proofs that you do early on in like a algebra course. You prove that a number only has one inverse. A real number. And it's very similar type proofs. Okay, next. And I guess that this is another proof that was a homework problem. Let A and Z n such that A is invertible. If B is equal to the inverse of A, then B is invertible and A is its inverse. In short, what we're saying here is the inverse of an inverse gets you back the number. If 7 was the inverse of 3, then 3 was the inverse of 7. So what's the inverse of its inverse? Gets you back 7. The inverse of 7 is 3, the inverse of 3 is 7, so the inverse of 7 is 7.
Mm-hmm.
Same thing happens with the real numbers. When I say 3 to the negative 1 to negative 1, that's just 3.
Mm-hmm.
Right? Or with any number we put in there. So that'll be perfect. And then definition. let A be in Zn where B is invertible, then now we finally have our definition of divides. A divided by B means A times B inverse. This only works where B is invertible. If it's not invertible, it doesn't work, it's not defined. Just like in the real numbers, we have one number that's not invertible. 0. So you can't divide by 0.
That makes more sense. Cool.
Same type of thinking. There isn't, if B is not invertible, definition doesn't work. So it's not defined for numbers that aren't invertible. It's only defined for numbers that are invertible. Okay. So that was the majority of the section. And then we have one more proof, which is the relatively prime. So the next thing we're going to show is that if a number is invertible in Zn, then that number is relatively prime with Zn. So the only reason that 3 was invertible in Z10 is because 3 and 10 are relatively prime. So let's write it out. So A in Zn is invertible if and only if A and N are relatively prime. Understand what we're proving?
Okay.
Okay, so 1. Let's do the forward case first. See how I have it written. We're going to assume A in Zn is invertible. Invertible. What does that mean? Then there exists a B such that A times B equals 1. There exists B in Zn such that A times B is equal to 1. Oh, oops, wrong times. But what is this A times B?
It's A times B mod N.
Right. Then A times B plus some multiple of N is equal to 1.
Okay.
You good with that?
Yeah.
Now remember,
That's for K in integers, right? Not necessarily K in Zn.
yeah, K is just an integer now. So maybe then there exists K such that A, what am I trying to show the relatively prime? A, so I'll write A times B plus N times K is equal to 1. You good with that?
Mm-hmm.
Okay, now we had a theorem last time that said A times an integer plus B times an integer equals 1 means that the GCD of these two numbers is 1.
Mm-hmm.
So A and N are relatively prime. Now I can't remember, maybe he mentions what theorem he uses here, so if you watch the video, you know what to go look up. Corollary 36.9. So this is by, which implies A and N are relatively prime.
Probably 30.
0.9.
Yeah.
I was gonna say, can't be, it was at the end, not the start. Okay. And I told you, we're gonna use that theorem over and over and over again. If I can express some linear combination of integers equal to 1, then that's your GCD,
How do you know about it?
if and only if.
A n rather than. My
You
question
can
is-
do it however you want.
So,
GCD of these two is 1, GCD of these two is 1, GCD of these two is 1.
That's what I picture.
Now, remember,
We didn't prove that though.
this is going to be the multiplicative inverse of this.
Okay.
So if this is relatively prime to m, obviously that is too. But if that feels weird, never mind. A times b equals 1.
Yeah.
So if a is relatively prime, if a times b equals 1, then b is the inverse of a and a is the inverse of b,
Okay.
right?
Yeah.
So they both have to be relatively prime with respect to n. Well, that's what we're showing. We only need to show it with a though, because you can pick a to be anything in the end.
Right.
But your intuition's right in that any combination of these are relatively prime with respect to each other.
How are we good? Did we prove that?
Yeah, that's what this theorem is.
Is that what we're proving right now?
We're proving that if this thing's invertible, then it's relatively prime with respect to n.
Okay.
This theorem says if you can express, take two integers, if you can express them as multiple, if there's two integers b and k that I can find that make this true, then a and n are relatively prime. Their GCD is 1. The smallest number I can get this to equal is the GCD of these two numbers.
How do you know that?
That's like what we started with. When we were, oh goodness, you needed to watch the previous lecture again.
I went to it. I didn't see it.
Oh yeah, I didn't get it up. I got sick Wednesday this week, so I couldn't go into the office, and I haven't been in yet. I'll get all the videos up tomorrow for sure. At the very least, you can reread your book and just remind yourself of all the theorems we
Okay.
went over. Because, yeah, can't stop or re-go over it. Okay, so that proves it one way. Now we need to prove it the other way. So the other way is let A in Z n such that A and N are relatively prime. And then we need to show that A has a multiplicative inverse, or a reciprocal.
Okay.
Right?
Mm-hmm.
Okay, so if these two are relatively prime, using that same theorem again, then there exist two integers, I don't know, x and y, such that ax plus ny is equal to 1.
Mm-hmm.
Let's see how I want to finish this. Basically, I want to say x is the multiplicative inverse. So, whatever the x is that you put here is a multiplicative inverse. let B equal X mod N. And then I'm finding this B is going to be the multiplicative reciprocal of A. So I'm going to show that this B is it, but do you see how the B is obviously going to be it? Because once you mod both sides of this by N, you're going to get AX mod N is equal to 1. So whatever that X mod N is.
Wait.
Look at this equation right here.
Okay.
Mod both sides of this by N. What do you get? This goes to 0. So you get AX mod N is equal to 1 mod N.
Oh, okay.
So whatever that, we already know that A is in Zn, so now we just need to get the X, whatever the equivalent is of X in Zn. And the way we're going to get that is by modding it by N.
Okay.
Good? Okay, so let B equal X mod N, then A X, well maybe I'll write then 1 is equal to A X can be rewritten as B plus some multiple of N. I'm rewriting this equation right here.
Right.
So A X can now be rewritten as B plus some multiple of N, right?
Right.
Plus NY is equal to,
1.
well, 1 is equal to, and I'm going to keep simplifying this side until I get it how I want it, is equal to AB plus AKN plus YN is equal to AB plus a whole bunch of stuff times N.
Okay.
Right?
Mm-hmm.
And then, let me equal that. Okay, so now I know what, I think I want to do this. This gives me, I want to solve for AB real quick. So, AB is equal to 1 minus AK plus Y times N. Because the reason I want to get AB is because then A times B is equal to A times B mod N is equal to AB is all that, 1 minus, is that an A? AK plus YN mod N
Which equals 1.
is equal to 1.
Oh, neat.
Okay. So all this to figure out what A times B equals, that way I know how to use this definition. Okay. So A and Zn is invertible if and only if A and N are relatively prime. So, since we know that we have to use, since we know that, I mean, this kind of gives us a way to start finding these things. We knew that whatever this X mod N was the inverse of A. Because now a common problem from here on out is going to be, what is the inverse of this number in this system? What is the inverse of 3 mod 10? That's easy when you can check all your numbers really quick. But now if I say, what's the inverse of 29 in Z327?
Right.
That's a much harder problem, a much harder question to answer. That's a harder problem to solve. And so the fact that we can use this formula tells us once again, we can use extended Euclids to find these things. So let's do an example of that. Like I told you, you're going to have to do extended Euclids on your test. And I told you that's for sure going to happen. And you're not going to be done by using extended Euclids. It's going to be something that you have to do as part of your problem to actually solve your problem. So if you're tripped up on that, you're in a lot of trouble. You need to make sure you know how to do this algorithm easy. Because the problem isn't going to be do the algorithm. The problem is going to be solve this, and you have to use the algorithm behind the scenes. Make sense?
Yeah.
So if you're struggling with that algorithm, you're in a lot of trouble. So let's do some examples. So find the inverse of 29 in Z sub 327. What is the multiplicative inverse of 29 in 327? Now, first we probably want to make sure that those are relatively prime so that we're not wasting our time trying to do something that's not possible. But the author gave us one that turns out it does have an inverse. So let's find what that inverse is. How do you do this? Start with Euclid's. 327 is equal to how many 29s?
Wait.
We gotta start by the GCD. We know that the GCD is going to come out 1.
Right, but why? Because we're finding the
We need to use extended Euclid's. Ultimately, we're going to get 29 times x plus some number times 327 is equal to 1.
We're doing that.
We need to find the x and y that satisfy this, and then this x, when we mod it by 327, is our multiplicative inverse.
Because y is...
Mod both sides of these by 327. This goes to 0. And so this, mod 327, has to be 1. So these two are relatively prime. Or these two are reciprocals of each other.
Okay.
Follow that?
Yeah, just trying to
Okay.
follow my head.
So let's do Euclid's. 327. How many times does 29 go into 327? Guessing 12 times.
I'm guessing.
Maybe
12.
11.
I was guessing 10 or 11.
Well, let's check it real quick. 29 and 12, what do we get? 8, 2. Did I do that right? No, I didn't do that right.
It's
It's
58.
11 times 29.
It's 11.
Yeah.
And what did it come out to?
319.
3 what?
319.
319, so a remainder of 8. So 11 29s plus 8. Then we've got 29 is equal to 3 8s plus 5. 8 is equal to 1 5 plus 3. 5 is equal to 1 3 plus 2. 3 is equal to 1 2 plus 1. Now remember, we need to rewrite all these in terms of their...
So we know it is in fact
Remainders.
prime.
Yeah, so it is relatively prime. So now 8 is equal to 327 plus negative 11, 29. 5 is equal to 29 plus negative 3 8. 3 is equal to 8 plus negative 1 5. 2 is equal to 5 plus negative 1 3. Okay, and then 1 is equal to 3 plus negative 1 2's. Right? So we start with this one. Pick the smaller of the two numbers, substitute in. 2. So substitute in for 2. So I'm going to restart over here. So 1 is equal to 3 plus negative 1 2's. Right? Which is equal to, collect all my 3's. How many 3's do I have? I have 2 3's.
2 3's. That's right.
And I have negative 1 5's. Right? Okay. Is equal to Take the smaller of the 3, which is 3. Take the smaller of the 2, which is 3. So we're using this substitution. We have 2 3s. 2 3s and -1 5s, right?
Yeah.
So
Negative 3 5s.
how many 5s do we have? We have -3 5s. And how many 8s do we have? 2 8s. And now, the smaller of those two numbers is 5. So we have -3 5s is 29 plus -3 8s. So -3 5s plus 2 8s, not 28, plus 2, plus 2 8s is equal to, I have
That's 11 eighths.
11 8s plus, now you get 3 29s. So that's equal to, I have 11 8s, 3 2 7 plus -11 29. I have 11 8s plus -3 29s. And that gives me, let's see, how many 29s do I have?
So that's negative 24 29s. Is that right?
Negative 124, is that what you said?
Yeah, that's right. That's right.
Negative 124 29s plus 11 327s. Okay, so this is equal to 1. So the multiplicative inverse, when I mod both sides of this by 327, this is 0, right? So this mod 327 is equal to 1 mod 327.
Okay. So I kind of lost what we're doing with this. So
We're looking for the multiplicative inverse of 29. 29 times what gives us 1?
okay.
Mod 327.
Okay.
And it's negative 124. But negative 124 is not in Z 327. So we need to add a 327 to that. What is negative 124 mod 327?
Does it mod 327? No.
Yeah, it does. It is. This is the same thing. When you mod 327, maybe you write a new
So
line.
it's negative 124. It's the remainder of. Okay. 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 Let's do it.
So 1 is equal to 2L3. Oh,
Why did you
You-
add 327?
okay. Let's think for a second. What's negative 2 mod 8?
It'd be 1 plus 10.
6.
Huh? Oh, okay.
Do you see?
I've lost my definition in my head.
Mod is the remainder.
Okay.
It always has to be between 0 and what we're divided
So
by, 8.
8 divided by negative 2.
This is when you take negative 2 is equal to some number of 8s plus the remainder.
Okay.
What are the numbers? Negative 1, 8, 6. Because this number has to be between 0 and 8.
Right. Okay. Alright.
Now remember, when you're dividing by 8, adding multiples of 8 doesn't change it.
Right.
So if thinking about that way starts to give you a headache, just keep adding multiples of 8 till it comes out. So if I would have given you something like, I don't know, negative 26
My
mod
question
8
is, are you going to 2 of
is the
3
same as 6.
because it's in Z 327?
Yeah, I'm gonna keep adding, or I'm taking, look, when I take negative 26 and I multiply by 8, it always gives me a number between 0 and 8. So when I mod by 327, if I take this number and mod by 327, is what I did,
Okay.
that's going to give me a number between 0 and 327, which is in this set.
And that's 203.
203, yeah. Did I do that wrong?
Why couldn't you have just kept it though? I don't see why you couldn't have kept it as -124.
Negative 124 is not in this set. I'm looking for the multiplicative inverse of this
Okay.
in this set. So if we were to write out some big freaking times table chart for Z327, then if we looked at 29, 327, their product is 1.
Okay. Yeah. Okay.
Okay, yeah, okay. Does it make sense what we just did?
Yeah. Yeah. It'll feel, I'll get more comfortable with it as I go, I'm sure.
Well, we're going to have to start using this fact really quick here now. Because now we're going to start solving linear equations. And if you see something like 4x is equal to 10, how do you find x?
Divided by 4.
You times it by the multiplicative inverse of 4.
Yeah, you
So it's very important that you know what that is. And so if I have 29x is equal to 37, and we're in Z 327,
You have to multiply it by 203.
then I know now that x is equal to 37 times 203
Yeah, 203.
mod 327, whatever that is. That's what x is.
Assuming that those are, what would that, isn't that congruence mod 327 though, rather than equals?
Let me be a little bit more explicit here in my. So if I know that 29 times x is equal to, I don't care, 13. Now I know that the x that satisfies this, what is x? X is equal to
13 times 203 mod.
is equal to 13 times 207, is that what it was?
203.
203. Times is in real number times.
Right.
Mod 327, whatever that number is, that's what x equals.
It's pretty straight.
That is the number in this set that satisfies this equation.
That's so weird.
And it could be some weird number like 221. 221 times 29 is 13.
It's so weird.
So that's where we got to go next. So that's what the next section is on. It's called, we're going to get to what's called the Chinese remainder theorem. Jeez, my throat is right out. I assume that I don't know. Does someone have a syllabus out?
Yeah. What are you looking for?
It's just what we're covering. I don't remember if I had the section by itself.
37 was last week's, 36 this week, doing 38.
Oh, that was this. Oh, jeez. It's warm.
Yeah, we do 38 and 39.
38 and 39, and we just did 37.
Yeah.
So we're behind.
Yeah.
So we have to do 2 next time no matter what. Maybe we'll touch into the heart of this and then let you guys get going with your homework and then kind of like what I did with modular arithmetic last time. So the next section, the Chinese remainder theorem, is all about finding solutions to linear equations. So let me write it up. So let's start out with a simple equation. What are the solutions to x congruent to 4 mod 11?
All the solutions.
Yeah. Give me one solution right out the door.
I'm trying to, sorry, need a,
Give me one number that is for sure equivalent to 4 mod 11.
that means that that number minus 4 equals 11, right?
That means that that number minus 4, 11 divides it.
11 divided.
Or that means that they have the same remainder when you divide it by 11.
4.
4! There we go. There's one. 4 is equivalent to itself. All right, that's good news. What's another one?
Every multiple of 4.
Really?
Wouldn't it be?
So you're saying 8?
No, that's not right. Everything forced, every time you add 11 from there.
So in short, it's 4 plus 11 times any integer. Any integer k you plug in there, and then 4 plus that is going to be a solution to this.
Yeah.
Good. Okay, let's do a little bit different one. What are all the solutions to 3x is congruent to 4 mod 11? Ah, shoot. That's a little bit tougher.
Yeah, isn't that what we just did, kind of?
Yeah, kind of.
Except it's not.
Very similar.
It's not. It's not modular arithmetic multiplication.
No, but it's using the same idea.
Well, it'd be any of those numbers divided by 3, wouldn't it?
What number, what numbers, when multiplied by 3 and divided by 11, give you a remainder of 4? 5. 15. You see what he did?
No.
5 times 3 is
15.
mod 11 divided by 11 has a remainder of
4.
4. So 5 is a solution.
Okay.
So we know 5.
Yeah. We will try to find our goal.
What else would work? Feel free to use your calculator if you want.
Not exactly sure where to start. What to start thinking about testing.
Kind of just start guessing and plugging and chugging and seeing what comes out.
Seventeen.
17
Yeah,
or 16?
I think 17. Yeah, 51 minus 4.
Oh, right.
No,
It's not right.
that's not right.
Oh, negative 17 is what I was thinking.
No.
You gonna make me manually plug one in?
No.
Alright, let's manually plug one in. Well, that's 3 times, I don't know, negative 6.
It's negative 18.
That's negative 18, but now let's multiply 11.
You get 7. I mean negative 7.
Plus 11 gets you to negative 7, so we gotta get a positive number. So maybe plus 22.
Why do you have to get a positive number?
mod.
Oh, it has to be, okay, okay.
So negative 18 mod 11 is
4.
4! Which is what we want. Okay, so negative 6 works. Should I randomly guess another one?
No.
Like maybe if you throw in a 27 here, it works. So I think you know what I'm doing. Now let's show that. Oh, I'm just adding multiples of 11. Same exact thing we did up here. No difference. Right?
Okay.
That's what I was doing. So let's show that when you have one solution to an equation like this, a multiple of that solution for whatever mod system you're in also works.
Okay.
You understand what I'm trying to say?
Yeah.
So I don't know how I want to write this. Maybe let's start with that exact example. Assume x1 is a solution to, what did we have? 3x is congruent to 4 mod 11.
Are we going to do a proof by induction or something?
No. We're just going to show that x1 plus a multiple of 11 is also a solution. So assume that x1 satisfies us. If I put in x1, it works.
Okay.
Then 3x1 plus k times 11, some multiple of 11.
Okay.
That's going to be equivalent to 3x1 plus 3 times k times 11 is going to be equivalent to 3x1 mod 11, which is going to be congruent to 4 mod 11. Shouldn't have done my mod 11, so we're good.
Did
you see that?
No.
Okay.
Oh,
Let's get rid of this
you
piece.
distributed.
Yeah, I just distributed it. So if I know a solution x1,
Okay.
if I know that 3 is congruent to x1, or 3 times x1 is congruent to 4 mod 11, then x1 plus any multiple of 11 will also work as I'm showing. So 3 times x1 plus any multiple of 11 is equal to 3x1 plus 3 times some multiple of 11.
Okay, I'm
Mod by 11.
I'm missing kind of where you get the first step. Kind of. Because it feels like you took out the mod 11.
I'm seeing if this is a solution now. Oh, you just write it at the very end when you're doing equivalence.
Oh, you do?
Yeah, I'm always doing mod 11. It's just to prevent writing it over and over again.
Okay.
So we're always in mod 11. This is equivalent to, is equivalent to, is equivalent to 4 mod 11. So you just throw it on at the end. That's why we only write it on one side of the equation up here, not on both.
Okay. Okay.
Good?
Yeah.
So now you see what I was doing? Nothing weird?
No.
Okay, so once you have one solution to any linear equation like this, I mean, we could have done this in general. We could have said if I have ax is congruent to b mod n. So if we're looking at this equation and x1 is a solution, then x1 plus any multiple of n is a solution. And we would do exactly what we just did. You'd rewrite a times x1 plus kn. What's that congruent to? That's congruent to minus or something? No, I'm not. Okay. It's congruent to a x1 plus a kn is congruent to a x1 is congruent to b mod n. you have one solution, you have infinite solutions.
Where,
I knew that x1 was a solution, so ax1 is going to be modded. That's why I'm coming back to solution. So if x1 is a solution to this, then x1 plus kn is a solution to this. It gives me the exact same thing that x1 gives me, which is a solution. I'm not sure where I'm losing you on
no,
that.
that's good.
Okay. So, okay, so let's make a little bit more generic of a statement. Instead of saying when we have a solution, then blah, 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 blah. Maybe let's go on break first before we get too far into this section.
Okay.
So go ahead, go on break. We'll come back, go over one more proposition, then show you how to solve systems of these equations. think what I'm going to do is just show you guys really quick how to solve system of linear equations this way. And then call it good. And then next time we'll prove it and then continue with the next section. That way you can at least start on the homework actually solving the problems, get through some, and then when you see the proofs, hopefully it clicks for you.
This is 38. 37.
I don't know. We have 38 and 39 left.
Right.
Yeah.
Then this is 38. Okay. So let's say we're looking at these two equations. And the question that we're trying to answer is, what number, mod 7 gives me 1, but mod 4 gives me 11? What numbers satisfy that? You with me?
Yeah.
So we're trying to find the number that satisfies that. Now from this top equation, we know all the things, we'll prove all the things that satisfy this, but all the things that satisfy this equation are the form 1 plus a multiple of 7. That's all the things that satisfy this equation. So the number that satisfies both these equations has to satisfy this equation, right?
Yeah.
So it has to be of this form. It has to be of the form 1 plus a multiple of 7. Okay? Now ignore what happens after this, but the point is, this equation gives us this much information about our hidden number. About our x. X at the very least has to be of this form. Good? Otherwise it wouldn't satisfy this equation.
So that's just one. That's saying every number x that when divided by 7 gives you 1.
Yes, every number that when you divide it by 7 has a remainder of 1
Remainder.
has to be of this form. So x, whatever x is, it has a 1 when you divide by 7, so it has to be of this form. So whatever x is, it has to be of this form. You with me?
Okay.
So our possible numbers for x so far are 1, 8, 15, etc.
Okay.
And you could have also gotten the negatives. Okay, so now let's look at this. So whatever our x is, it has to satisfy this. So we know this much information about our x. So substitute what we know x has to be equal to here. You with me?
Mm-hmm.
Okay. So 1 plus 7k has to be congruent to 4 mod 11. Subtract 1 from both sides. 7k has to be congruent to 3 mod 11.
So my question, we never really went over what it means to be congruent. Like we've gone over mod, but not really congruent. So does it work the same way? Can
We
you
did
subtract?
this before we did mod.
No, we did it at the same time.
No, we did this one first. This goes clear back to congruence classes.
We did equivalence relations.
We showed that this was an equivalence relation for a particular mod, like mod 2.
Okay, will you remind me what it is? What is congruent mean?
A is going to be mod n. The definition of this is b, or n divides a minus b.
Right.
That goes way back, right?
So does it work the same way that you can subtract both sides, you can multiply both sides?
Yeah. If I decrement both these numbers by 1, or increment them by 1, then their difference is still the same. I didn't change this.
Is there such a thing as congruence without the mod?
Yeah, but it depends on your context, like congruent triangles.
I mean this context.
Congruence depends on your context, what it means.
Okay.
So I don't know how to answer your question.
Okay.
But A is equivalent to B mod n. Have I been saying is it congruent?
It's congruent, yeah. Pretty sure. That's what it said in the book.
Modular congruent or modular equivalent? I think you're right. I think it's congruent. Anyways, this is true when this is true. And if I add the same thing to both of these terms, their difference is the same.
Okay.
Right?
Yeah. Okay. Just wanted to check.
Yeah, that's fine. Another way to do it is, if you don't like thinking about this way, then you can think about it as, this is true only when 7k mod n is equal to 3 mod n. right? We have that theorem where instead of thinking about it this way, we can always think about it this way.
Yeah.
Do our algebra here, and then go back this way, if that helps you think about it. Because here we're just using an equal sign, how you're used to using an equal sign. Nothing weird. This isn't quite an equal sign. So, you can't think about it that way too, if that helps.
That's kind of what.
But you're
I'm used to equal meaning, you know, these two statements are equivalent, whereas congruence, I'm not really sure what that means in my head, like intuitive.
when you mod them by 11, they're equal.
Okay.
Okay. So 7k is equal to 3 mod 11. Or it's congruent to 3 mod 11. So when we multiply by the same thing, it's still going to be equal. And that's 7's inverse. We don't know what that is yet, right?
Yeah.
But 7 times 7 inverse, whatever that is just going to leave k here. So you have to find what is the reciprocal of 7 mod 11. When the numbers are small, it's easiest to just like start guessing. Don't do Euclid's to find this. So the inverse of 7, you just play with some numbers and it turns out it's 8. 8 times 7 is 56, which is 1 more than 55, which is a multiple of 11. So 7's reciprocal is 8. You with me on that?
Good. So a way you can find that is 7 times 11 plus 1. Is that how you would solve for an inverse?
The way I did it is I said, what 7 times what when I divide by 11 gives me 1. And just started thinking about some numbers. It's like obviously not 1, 2, or 3. Just think about 8. I mean, it's kind of like a plug and check method. When this is small, plug and check's easier than doing Euclid's. When it's big, Euclid is easier. Anyways, so 8 is the multiplicative inverse of 7. So plug that in. 3 times 8 is 24. Mod 11 is 2.
So at that point it wouldn't be 2 mod 11, it'd be just 2, right?
2 mod 11.
It'd be 24 mod 11, wouldn't it?
24 mod 11 and 2 mod 11 are the same thing.
Yeah.
Every number that, yeah, you're with me. Okay, so then if k is equivalent to 2 mod 11, what are all the numbers that satisfy that? 2 plus any multiple of 11.
Yeah.
So k has to satisfy this property. So x had to satisfy this, where k has to satisfy this. Plug that in for k, so x has to satisfy this. So any number of the form 15 plus 76 plus multiple 77 will satisfy both these equations.
Huh.
Now, as a general rule, once you find a solution to one of these, once you find the solution to both these equations, it's going to be that solution plus any multiple of their mods. So the fact that 77 is a product of 7 and 11 is not a coincidence. That will always be the case.
Is there a way you can find a pattern where it's always, or my question is, do you have to solve this every single time, or is there a way you can just find a pattern that makes it easier?
You have to solve it. In the same way that you solve, I mean, this is very similar to solving to a system of linear equations. You solve the first equation in terms of x, and you plug that into the next equation and get your solution. Right?
Mm-hmm.
In like your algebra class. So let's do one more complicated one, and then we'll start homework. So now we're looking for the x that satisfies all these. It's congruent to 3 mod 9, to 5 mod 10, and to 2 mod 11. What's the number that satisfies all that? Or what's the set of all numbers that satisfy all that? That's what we're going to find. So since x is congruent to 3 mod 11, we know that x has to be of the form 3 plus some multiple of 9. Right?
Yeah.
So now, plug that in here. Let me write this equation to the side for a second, and we'll come back and get it, so I can work with this. So now, let's substitute that in for x here. So I know that x is congruent to 5 mod 10, right? That's 5. Which gives me 9k. 9k is congruent to, subtract 3 from both sides, 2 mod, I'm going to stop writing the mod 10. I'm just going to write congruent and keep going with it. So that means 9k is congruent to 2, right? Now we want to get the k by itself, so we need the multiplicative inverse of 9, which is what in mod 10? What's the reciprocal of 9 in mod 10? Don't look at the big chart. 9! Okay, so we're going to multiply both sides by 9, and we're going to end up with k is congruent to 8t, which is congruent to, when we're mod 10, 8. Right?
Yeah.
So k is equal to 8 plus some multiple of 10. So plug that into what we know about x. So x is of the form 3 plus 9 times 8 plus some multiple of 10 is equal to 9 times 8 is 9 times 8 is
72.
plus 3 is 75. Oh, 90, J. So now, any x that satisfies this solves both these equations. Now we need to get one that also solves this. So we have 75 plus 90j is congruent to 2 mod 11. Right? Now let's clean up these numbers real quick so that we can make it more usable. What is 75 mod 11?
1.
9.
9.
1.
Oh, yeah, 9. You're right, sorry.
9 plus, what's 90 mod 11?
2.
2. Is congruent to 2 mod 11. Subtract 9 from both sides, and we get 2j is congruent to, what goes here?
-7.
Which is?
4.
There you go. 2j is congruent to 4 mod 11. Now, what's the multiplicative inverse of 2 mod 11?
That means what mod 11 times 2 equals 1? No.
2 times what, when you mod by 11, gives you a 1?
6.
6.
6.
There you go.
6. 6.
6.
6.
Okay. When it's 2s, it's real easy, right? You just gotta get one higher than that.
Yeah.
6. So multiply both sides by 6, and we get j is congruent to 6 times 4 is
24.
mod 11 is
2.
2. So j is of the form, what letter are we going to use next? N? Sure. So j is of the form 2 plus some multiple of 11, right?
Okay.
So plug that in for j. So we knew that x was equal to 75 plus 90j. So x is equal to 75 plus 90 times 2 plus 11m, which is equal to 180 plus 75 is 255, did I have that right? Plus 990m. I guess we could.
Or m can be any integer.
M is any integer. Put any integer m you want in, whatever number you get out, satisfies all three of those equations. So in short, the Chinese remainder theorem proves that we can do what we've been doing. We've just been doing it and saying, look, it works. 255, 990. Yep, okay, so we did it right. So that's solving these, and then we'll prove next time that what we were doing actually solved them. So use the rest of the time to do your homework.
Next section.
Huh?
We're not gonna do the next section.
Not gonna do 3 sections in one day.
How are we gonna catch up?
We have days to kill.
I thought we only had 1 day to go.
No. No, we have many days to kill.
Really?
We only have 2 more chapters of material to go over, right? We had, I think, 3 days to kill, so I think we still have 1 more day cushion. Unless we already lost a day. Did we already lose a day?
Yeah.
So this might have been our last cushion day that we had.
Yeah. That means the last week of school will be taking time. Reschedule.
Just the way we like it.